When this moving red ball collides with this stationary blue ball, Newton's third law tells us that they're going to apply equal and opposite forces on each other. So this is the force of the blue ball on the red ball, and this is the force of the red ball on the blue ball, the equal and opposite. And because they're both experiencing the same collision, the time will be identical for both of them, of course. So what this means is that the force multiplied by the time is equal for both of them. So the F delta T for the red ball is equal, but opposite in direction to the impulse on the blue ball. And because we know that impulse equals momentum, what we know is that the change in momentum for the red ball is the same as the change in momentum for the blue ball. So delta P for the red ball is equal to the negative of delta P for the blue ball. And so the sum of all the change in momentums is 0. Any momentum lost by the red ball will be gained by the blue ball, and so we say that momentum is conserved. So how do we use this? So we know that the momentum before a collision will be the same as the momentum after a collision. So here is a big green object moving towards a big orange object. The green one weighs 12 kilos, the orange one weighs 20. With these velocities here, you'll note that that's a negative because it's in the opposite direction, so I'll define that direction as positive. So this is the situation before the collision, they're moving together. Afterwards, the green object is stationary and the orange object has some velocity we don't know. We're going to use conservation momentum to predict that. So in my equation, I'm going to set the left-hand side of the equation to be the momentums before the collision. The right-hand side of my equation will be momentum after the collision. So mass times velocity for the green object plus mass times velocity for the orange object will equal the mass times velocity of the green object after the collision plus the mass times the velocity of the orange object after the collision. Now you may be comfortable after a while just leaving this term out because obviously this is going to be 0. Any stationary object has 0 momentum. And so when we simplify this, we get 60 minus 40, so we have 20, call that kilogram meters per second, equals 20 times V. So 20 kilograms times V in meters per second. And so solving for V, we see that V is 1.0 meter per second. That's come out as a positive answer, and so we know that that is 1 meter per second in that direction. So it's important that you set your work out correctly, that you set out this side of the equation, the sum of all the momentums before the collision, and this side of the equation, the sum of all the momentum after the collision. You can, if you feel comfortable, leave out any terms for stationary objects because they are going to have 0 momentum, and you'll be able to solve to find any missing terms. Momentum is conserved in any collision, even when it doesn't look like it is. So here is a car moving towards a wall. If we know that that car is going to hit the wall and come to a stop, it's not going to move the wall at all, then it doesn't look like momentum has been conserved. But what has actually happened is that the car has, let's say, some large amount of momentum. It will transfer the entirety of its momentum to the Earth. So even though it doesn't look like the momentum is conserved, the Earth has moved ever so slightly in response to this. The car has transferred all its momentum through the wall to the Earth. And so that's how momentum is conserved in a collision like that. But generally, if there is no outside forces acting, it's what we call an isolated system. You may see it referred to as that. Momentum will always be conserved. The momentum before the collision will be equal to the momentum after the collision.